One of the common methods for analyzing Zane spectra of transition metal K-edges is to measure the relative intensity of the pre-edge peaks that correspond to the crystal field splitting of the mixing of the metal d electron orbitals with those of the oxygen 2p orbitals. In this video, I'll show you how you can fit and analyze pre-edge peak intensities. Hi, I'm Matt Newville, and this is part of the video series for using Larch for XAFS analysis. The pre-edge peaks of the first row transition metal K-edges are particularly rich as they clearly display intensities that depend very strongly on bonding environment and symmetry to the oxygen ligands. These pre-edge peaks are below the continuum 4p level and so are partially bound to the metal atom, but display hybridization from the ligands, typically oxygen. While absorption of the 1s core level most strongly goes to a p level, the unfilled d electron orbitals will hybridize with the oxygen 2p levels, so that these hybridized electron orbitals, the EG or T2G of crystal fields theory, typically will have some p-like character that overlaps with the metal 1s level at the core, and so gives some intensity. This usually makes the pre-edge peaks weak relative to the main edge from the 4p level, but it also can give peaks that are very sensitive to the nature of the electronic bonding and chemical bonding to the oxygen neighbors. As an example, when the metal is highly oxidized, say titanium 4+, vanadium 5+, chromium 6+, or manganese 7+, the oxygens will be tetrahedrally coordinated to and the hybridized levels will have a very strong p-like character, which gives these pre-edge peaks a very strong intensity, as large as the main edge itself. Even for mostly or partially octahedral sites, the pre-edge peaks can be readily analyzed to determine oxidation state and chemical environment. Here, we'll look at the pre-edge peaks of iron K-edges and analyze them to get the centroids of the two peaks in question. While many folks have done this over the years, this example here follows the work of Elizabeth Cottrell and co-workers, and who have carefully calibrated the centroids of iron pre-edge peaks in a variety of systems with Mossbauer results. The data I'll show here is from some of those kinds of studies, and I've mostly hidden the details of the actual samples, but if you're interested in following more of this sort of work, I highly recommend the work of Cottrell et al. For this. So let's start by reading in some iron XAFS data on some basaltic glasses. So completely glassy samples. Here we have several spectra, and I'm just going to select them all and import them all. They have a range of, select all, plot the selected groups as normalized mu. They have a range of pre-edge peak intensities, and you can see the main edge is also shows some shifts as if the oxidation state changes quite a bit between these samples. I'm going to just a little bit worry about the normalization for these. This is good enough for the pre-edge peak analysis, but here I'm just going to make sure that we've taken, for all of these, we've taken the normalization range from 100 to 200 volts above the edge, about the extent of the data. And I'm just going to assert that that should be a constant, copy that to all of the groups and replot. That looks better. Now the normalizations look like that. Those are pretty consistent. And we can go on to do the analysis. To do that, we'll start with one spectrum and analyze this. We'll go to, in Larch XAFS Viewer, we'll go to the pre-edge peak tab, and here it shows what array we're going to fit, the normalized mu for this data set, and we're going to fit between -20 and 0 relative to the edge. I might actually adjust that a little bit in a second, but to start with, we're going to fit a baseline that takes care of the main edge. Now we could use an arctangent or error function or other sigmoidal function. Here I'm going to use a line plus a Lorentzian, where the Lorentzian will try to account for and match the 4p level of the iron. So I'm just going to hit fit baseline, and I'll show you what all of this is doing then. Here we've said now it's filled in the numbers in absolute, and I'm going to adjust these. Let's start at 7100 just to make this even. I'm going to bring this down just a little bit also. And then, so what we've done is we fit a line plus the Lorentzian between these two values. We fit that. but ignoring the range here, this baseline skip range. So where these large black dots are, I can update those a little bit. Again, this is not vital to get this perfect because this is just our starting baseline. And after this, we'll do real analysis of these peaks. But for now, this is a decent fit of the baseline. And it shows a couple of things. So here down in this section, down in the lower part of this panel, there's a tab section with a value called, or a tab called B peak, baseline peak. That's a Lorentzian. It has a center of 7117, so over here. So that's the Lorentzian that accounts for the iron 4p. And then we have a polynomial that's just a line. So we have a line plus a Lorentzian, and that's what fits this. And when we've done that fit, we've ignored where the pre-edge peaks are. Already, you can see that the gray lines show the approximate area of where the fit was done, and then this pink line shows the centroid of the data minus the baseline. So if we just subtract the data, subtract this baseline from the data, then we have these peaks, and we can estimate the centroid, and that's it, around 7112 for this data set. And that'll hold out. That will be shown to be robust through all of this analysis, but we can do a slightly better job at measuring that. So to do that, we're going to try to model these peaks. Within this form, we can specify several sorts of models that you might want to fit data to. But here I'm going to pick peaks, and we'll start with Gaussian. So if I pick a Gaussian, then a new tab in this list shows up, and this is called Gauss 1. The values are not yet initialized. The Gaussian amplitude and center are 0, so we want to select those from the plot. So I'm going to click this, pick values from plot. I'm going to click this, and then hit twice in the region where on the plot near where the peak is. And that will give a decent guess for how big and where the Gaussian should be. I should say that works exactly opposite from from using these pins where you click on the plot and then select the pin to take the last value selected from the plot. Here you pick the button first and then select twice on the plot. So here this reports that the Gaussian center is around 711.1.6, and there's an amplitude in sigma. And we could, for example, hold these fixed or constrain them in other ways. For now, I'll leave them but we can also set boundaries. So I'll just say that the amplitude should be positive. These peaks are positive. Let's just enforce that they will be positive. So now with that initial guess, I can just say fit this group. And that will show this as the best fit. Again, with only one Gaussian, this is not the best fit we're going to get. But this also brought up this page of pre-edge peak fit results. And here we see fit 1, the most recent one, shows a centroid value, very close to what we had before, and then also the parameters for the Gaussian center and sigma, and it also reports a full width half max and a height. Let me plot this again and zoom in on this, and because I want to show you the height reported here is actually the maximum intensity of that Gaussian of around 0.05. The amplitude here is the amplitude of the unit normalized Gaussian. That is the area under the curve, or the weight of that Gaussian. And so the centroid is just the amplitude times the center of that Gaussian divided by the sum of the centers. So, but by the sum of the amplitudes. So the centroid is easy to calculate in that way, and the amplitudes are not the most extreme height. That's the height, and there's also the full width half max of that peak. Sigma being larger than sigma by a factor of 2.3 for a Gaussian. Okay, so that's a start for that, but we want to go back, and clearly we want to add a second Gaussian to this model. So I'll go back to our fitting panel and add another Gaussian. So just now we have Gauss 1 and Gauss 2. We'll have to guess where this one is too, so we'll do the same thing where we pick values from the plot, and I'll click over here for the second Gaussian. That looks good, and I'll do the same thing. I'll make this one positive. And I can plot this current model. That's our 2 peaks. The second one was pretty low in intensity, so I might want to increase that intensity. I'm just going to, just for now, I'm just going to make that a factor of 10 larger just to see where it would be. And now that's clearly too big, but okay. Now we have 2 peaks, one at 7112 and one at 7111.6. That looks like that probably will be fine. We could set these values to have upper and lower bounds, just so they are not easily swapped. So I might say that the Gaussian 1 center can't be bigger than 7113, and the Gaussian 2 center can't be smaller than 7112. That still allows a little bit of overlap, but clearly the peaks won't both be in between there. So if I now fit the current group, I get a fit that looks about like this. So that looks a little bit better for a fit. And now go to our fit panel page, we see that chi-square and chi-square reduced got significantly better, almost an order of magnitude better, and we have values for the center of the 2 different Gaussians. And again, when you click on any of these, you also get the correlation with the other parameters displayed below. So now we have a centroid that's 7112 plus or minus 1. So that's staying pretty consistent. No matter how we do the fit. So we can plot this fit again. We can do a couple of things here. We can plot baseline subtracted. That will show the data minus the baseline, and the fit and the 2 peaks minus the baseline. So that's the baseline subtracted data. And or we could also plot with the residual, which will bring up a new window that shows the data, the best fit, the baseline, the 2 peaks, and then in the panel below, the misfit to the fit. And you can see that there's some structure here, which is something we'll come back to in a bit. We can also adjust, at this point, we could also adjust the fit ranges. This is probably way too, asking way too much to fit that a line and a Lorentzian all the way down there. So we could adjust that, make that go up a couple of volts. I'll just click this up and just redo that plot, or redo that fit from here, from 7102, fit this, just to get, like, we're happy with that, and then plot this residual. That looks reasonable. It's done a pretty good job. And again, yeah, we could adjust that. But I think the real story for doing any better is that there's some structure here in this misfit that we'll want to come back to. But this is pretty good. This is a good start. And so what we might want to do here, the next thing we might want to do is say, let's fit all of the spectra that we have. So I'll just click on this button that says fit selected groups, and that will apply this same model to all of the groups and bring up the results. So here are the results for all of those. So this is for HL7. I can do the same thing. I can plot that. That's also shows a decent fit, but some systematic residual. There, the data, the peaks are clearly moved around in the opposite directions, and so on. And we can just inspect that all of these fits are okay. These are all okay fits. There is some noticeable residual, at least in the ones that have the cleanest data. There are some that are sort of consistent with the noise level, but the data is noisier. So this might be what you would want to do, and now we can do a couple things to save the results. We can save the model, so we can save the entire set of parameters that built this model with a Lorentzian and a line to represent the background and 2 Gaussians. And then we could read that back in so that we can reproduce that fit. So I'll save that as like my peak, and it's a model file. It's a blob of JSON text that accounts for that. But here we could go back here and load a previous model, so we could load that again, or you could send that by email to your coworkers or interested parties. From here I can also save the fit components for the current group. So this is MS4. I'll just save this as a file, as a text file, a plain text file. That's here, that got saved. If I go and read that in, that becomes this file. I'll bring that over here. That's this file that's got a lot of columns in it. All of the fit results are described here. All the fit statistics are listed. And then here are columns of energy and data and the best fit, the initial fit, the residual, and then each of the components of that model. So if you want to replot those in using a different software tool, you can do that. So that's also like a complete record of the fit. And then also, but that's just for that one data set, and you might want to say, let's save the parameters and statistics for all of the fitted groups together, and that will save a CSV file, and that's called peak results. I'll just leave it like that. I'll save that and show you what that data file looks like. If I open that, it will look like this, where it has a description of the model, and then rows with data set and the number of variables and so on, and all the fit statistics, including the centroids and the uncertainties in all of the fitting parameters. So that's also then, that's not quite the paper, but that's the table that goes into the paper. But let's go back and look at these fits again, especially the better ones, and notice this misfit that we have here. And I think that that's actually due to the fact that the peaks aren't simply Gaussian. So let's try. I'm going to go here and alter the model by deleting the components for Gaussian 1 and 2. I'm going to delete those components. And I'm going to use now Voigt functions. A Voigt function is the convolution of a Lorentzian or Gaussian that accounts for both the natural width of the line and also some energy resolution from the finite resolution of the monochrometers used at real beam lines. Even though the resolution is pretty good for this data set, we can see that the result is a convolution of a Lorentzian from the atomic transition and a Gaussian from the monochrometer. So here I need to do the same thing, initialize the value. So I'm going to pick from the plot, and come over here and hit twice. That looks pretty good. It's about the same starting value, and I'll do the same thing for the second one. Start from here. And now, so plot that model, that's the starting value, and fit that. And now here in this list for WB3, we have the models that were the Gaussians. We're going in order, with one being the most recent. So this was our model with the Gaussian. It had a reduced chi-square of 1.6 times 10 to the minus 6. A reduced chi-square with the Lorentzians is a factor of 3 smaller. Maybe more than that. And so let's plot that with the residual. And you can see that now that's the same data set with the Gaussians. There was this systematic periodic oscillation in the residual, and with the Voigt functions, that's mostly gone away. So that's a better fit from the statistics. Then the measure of the centroid and all of the parameters will be better. So that's really a better measure of a better model for the data. And in fact, now you can see that if there's any kind of misfit, looks like a systematic error at the lowest energy, which might be where you would want to add a third peak for an actual quadrupole term. But we'll leave that for later. I think this is good enough, and we could now that we have this model with a peak and a line for the baseline and 2 Voigt functions, we can say fit all the selector groups with that model. That will come up, and we can go through these, and let's make sure that those all fit. Okay, here's that data set, still a good fit. This one, again, here we have fit number 2 is now the previous one, so that's the Gaussian, and the fit 1 is the most recent, Lorentzian. So for this data set, there was a modest improvement, but the data is fairly noisy, and that looks like a very clean fit. Here again, now we have a factor of 3 improvement or so in fit statistics. Looks like a systematic misfit at the lowest energy, and we're really seeing that there's a consistent story here. Let's just make sure that all of these are, again, reduced chi-square is better. And we have good fits for most of these. Let's see if all of them are good fits. They all look pretty good from here. That looks pretty good too. So I think we've done a reasonably good job at fitting all of these spectra with 2 Voigt functions and a baseline that is a line plus a Lorentzian. And again, we can save these fits as any in any of the either the model or the CSV file of the results. So I think that's a good place to conclude for how to do pre-edge peak fitting, and I hope that gets you started. If you have questions, comments, or suggestions for how to do a better job of this or what else could be done, leave them in the comment section below or contact me. And I hope that you found that helpful and that gets you using pre-edge peak analysis in your work. Thanks.